Hi everyone. Last episode we discussed why we need a Hilbert space to deal with an infinite vector space. In the definition of a Hilbert space, we mentioned an inner product and said it was basically like a dot product. In this episode, I want to further explore this idea and really nail down what the inner product is. Before delving into the inner product, let us take a second to remind ourselves why the dot product is a useful concept in vector spaces. First, the dot product allows us to define a notion of angle and orthogonality, aka being perpendicular. Remember that we have the following equality for the dot product, which essentially tells us that the dot product is a measure of the angle between vectors. Importantly, if two vectors are orthogonal, their dot product is 0. Next, the dot product gives us a way to define the length of an abstract vector. With our typical arrow approach, we can calculate the length of a vector using the Pythagorean theorem. Note that this is the same as the square root of the dot product with itself, so we can define it in terms of the dot product. Defining the length of a vector in terms of the dot product is really useful since it can be used on vectors that aren't necessarily arrows. These are notions that we would like within our quantum vector space. So we want to find a way to take the dot product and abstract it to a concept that we can use in any vector space, not just arrows and columns of numbers. This is exactly what the inner product is. So how should we define the inner product? At its core, the inner product is a map that takes in two vectors and spits out a number, which might be complex. Now this notation is sort of clunky, and in quantum mechanics we put a much cleaner notation for the inner product, which is done by putting two kets together as shown. Really quick, I have one more thing to add before we define the inner product. With looking at addition and scalar multiplication of kets, it is common and sometimes useful to write them as a new ket like this. This might seem weird at first, but consider it a label for the new vector that resulted from the operation shown. Now, remember that we want an inner product in order to define things like length, which should be a real positive number. In order to do this, we need to put some rules in place. First, the inner product should be linear in the right-hand position, meaning for kets psi, phi, and zeta in scalar A, we have the following. This just follows our intuition from the dot product. In a bit, we'll show that we have a different rule for the left-hand position. Next, what happens when we flip our inner product, meaning we do this? You might think we can just have it be equal, but let's see why this is an issue. Assume the vector phi has an inner product with itself equal to 1. Now let's calculate the inner product with itself of the new vector I times phi. We can take out the I from the right-hand slot. Now, assuming flipping the inner product doesn't change anything, we can flip the two positions. Take out the I again, and remember that we assumed the inner product equaled 1. Thus, we get that the new inner product is equal to -1, but this is a problem. Remember that we wish to define the length of a vector as the square root of the inner product with itself. In this case, we get an imaginary length, which doesn't make sense. The way we fix this issue is by adding the condition that when we flip the inner product, we must add a complex conjugate. If we go back into our previous example and add this condition, we now get the following. Take a second to follow each step. See how the complex conjugate gave us a 1 in the end, and hence a real vector length? Last, we need one more condition to ensure that the magnitude of vectors makes sense. We must impose the fact that only the 0 vector has 0 length, meaning if your vector is non-zero, then its length must be greater than 0. Common sense, right? And that's it. We now have the formal definition of the inner product. Do you now see how these conditions are just the dot product with a few extra rules to make sure we can still define length? Hopefully the inner product is not so mysterious anymore. Now, what if we had a linear combination on the other side of the inner product? Well, we can just apply our current rules. We can first flip it, giving us the complex conjugate. Then we can use the linearity of the right slot, making sure to distribute the conjugate accordingly. Then we can flip the inner products again, which cancels out the conjugate. So what we get are inner products with conjugated coefficients. So although the right slot acts linearly, the left slot acts what we call antilinearly, where the coefficients are conjugated. Great, let's establish a few more things about the inner product. Following our intuition from the dot product, we will define the magnitude of a ket to be the square root of its inner product. And we will say that two vectors are orthogonal if their inner product is 0. With this, let's now use the inner product to see how it works in our quantum vector space. First, let's say we have an orthonormal basis, which means that each vector has length 1, and they are mutually orthogonal. It's common for physicists to combine these two conditions into one using the Kronecker delta. The Kronecker delta is a very simple object with two indices. When the indices match, it equals 1, and when they don't, it equals 0. So, the orthonormal condition can be condensed into one statement. Check yourself to see that this is true. So, if we have an orthonormal basis, we can expand an arbitrary quantum state in this basis. Now, how would we get a particular coefficient? Well, because the vectors are mutually orthogonal, we can use the inner product to single out the coefficient that we care about. So if we want the second coefficient, let us take the inner product with the second basis vector. Using the fact that the inner product is linear in the right slot, we can move the inner product into the sum. Now let's write the inner product as a Kronecker delta. Remember that the Kronecker delta only equals 1 when the indices match, equaling 0 otherwise. So when we sum over a Kronecker delta, all elements of the sum will be 0, except the one that matches the index. So what we can do is collapse the sum, and anywhere we see an I, we just replace that with a 2. So what we get is our coefficient. It may have seemed excessive to use the Kronecker delta there, but trust me, it is a powerful tool to get used to. To see just how powerful it is, let's look at the inner product of two vectors. Like before, we expand both in an orthonormal basis. To simplify this, let's remember our rules. First, remember that the inner product of a sum of vectors is the sum of the individual inner products. So we get a double sum. Next, remember that the right slot is linear, so we pull out the b coefficients. And on the other hand, the left slot is antilinear, so we pull out the a coefficients and conjugate. We assumed this was an orthonormal basis, so we can write this inner product as a Kronecker delta. Now, remember what we said. The Kronecker delta is non-zero only when I equals j. So in the inner j sum, the only non-zero term will be the term that matches the I index. So we can collapse the inner sum and replace j with I wherever we see it. The remaining Kronecker delta just equals 1. See the technique? The Kronecker delta allows us to collapse sums easily. We just have to match the two indices. Awesome, and look at what we're left with. It may look weird, but let's say all the coefficients were real numbers. This means the conjugation doesn't do anything. And we are left with the following. Look familiar? This is the dot product. We made no mention of the dot product in our definition of the inner product, yet here it is. So hopefully you see that the dot product is what you get when you look at the inner product in a particular orthonormal basis. Now, we have made a lot of progress with the inner product, but so far we have only looked at the inner product with discrete linear combinations. What if we had a continuous linear combination, like we did when we looked at the linear combination of position outcomes in episode 2? We will delve into this next episode, where we will go in depth on the Dirac delta function and derive the inner product for wave functions. Thanks so much for watching this episode.